Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to everyone. Let me know quickly in the chats, people. Every one of you. Let me know quickly in the chats, people. If all of you can hear me, if I am perfectly audible and visible to every one of you. Welcome back. Welcome back, guys. Welcome back. So, my dear students, as you all must be knowing, today it's going to be the second session of the chapter Atomic Structure, right? And if you remember, in the last session, we discussed about some basic things related to atomic structure, like the cathode ray experiment, anode ray experiment, Millikan's oil drop experiment. We talked about the Thomson's model. We discussed the Rutherford's model. We saw the distance of closest approach, etc., right? All those things were basically discussed in the last session. So what all things I'll be discussing in this particular session? My dear students, there is a lot to discuss. Basically, it's a big chapter, right? And it's an important chapter too, because it is related to your atomic physics as well. Okay. So in the today's session, we shall be discussing about the Planck's quantum theory, number one. Number two, we shall be discussing about the photoelectric effect and its applications, all the questions related to it. And at the same time, we shall be starting the Bohr's theory as well. Okay, so these are basically the topics which I shall be covering in the today's session. So are you all ready for it? Are you all ready for it, my dear students? Quickly, let me know in the chats. Are you all ready for it? Quickly, people. So we shall be starting with the Planck's quantum theory, and we shall be discussing the photoelectric effect, and at the same time, we shall be doing the Bohr's atomic theory as well. So without wasting a lot of our time, let's get going then. Let's get started. But before that, the ones who have not liked the session yet, I would want every one of you to like the session. Share this particular video with everyone, right? Whosoever is preparing for NEET 2024, this particular session is for every single one. And my dear students, at the same time, if you have not subscribed to the channel yet, I would want every one of you to subscribe to this particular channel as well. Okay? Perfect. So let's get going then. Let's get started with the Planck's quantum theory. So my dear students, what this Planck's quantum theory exactly is all about. Try to understand, right? Step by step, I'll let you know the things. First of all, the theory which we are going to talk about, the Planck's quantum theory, let me first of all tell you, this Planck's quantum theory, it supports the particle nature of light. It supports the particle nature of light. As you all must be knowing till now, since you already must be knowing that light has got the dual nature. It has got wave nature as well as particle nature. This particular theory which we are going to discuss today, it is going to support the particle nature of light, right? It's going to support the particle nature of light. Point number one. Point number two. As per Planck's quantum theory is concerned, energy is transmitted. Energy is transmitted in the form of small packets, or I can say in the form of small units. And those small packets or small units are called as quanta. What it exactly means. Try to understand what exactly I'm going to talk about. See guys, as per Planck's quantum theory is concerned, energy is basically transmitted in the form of small packets, or you can say in the form of small units, and you call those small units exactly as quanta. Now, what it exactly means? My dear students, for example, let's say this is some source of energy, right? Let's say this is some source of energy. The source is continuously emitting energy in the form of a radiation. Assume that this particular source, it is continuously emitting energy in the form of radiation, right? Now, as per Planck's quantum theory is concerned, energy is transmitted in the form of small packets. So, my dear students, let me tell you one simple thing. This particular source of energy, since it is emitting radiations, radiation is a form of energy basically, right? Since this particular source, it is emitting radiations. Now, those radiations, for example, let's say this is one of the radiation which I'm showing over here. My dear students, the radiations, whatever radiation it is, radiations, they consist of small packets. They consist of small packets of energy, right? And these particular small packets, I mean, one particular small packet is something which we call as quantum, right? And a lot of these small packets are what we call as quanta. Perfect. So very simple and basic thing. Whenever I'll be talking about Planck's quantum theory from now onwards, only one thing should strike my mind. What is that? Energy is transmitted in the form of small packets, right? Small units, and these small units are what we call as quanta. For example, this was the source of energy which was continuously emitting radiations. Perfect. Let me show you one of the radiation over here. Let's say this is the radiation. It consists of small units of energy. It consists of small packets of energy. One packet over here is something which you call as quantum, and a lot of packets together are what we call as quanta. Perfect. My dear students, particularly if I talk about the light radiation, So I'm writing in case of light radiations. In case of light radiations, let me tell you, in case of light radiations, these small packets of energy are what we call as, these small packets, these small units are what we call as photons. These small packets are what we call as photons, right? Sound clear nahi hai. Guys, am I perfectly audible? Let me know once in the chats with yes or no. Am I perfectly audible? Say yes or no in the chats quickly. Say yes or no in the chats quickly. Yeah? All right. So majority is saying I'm perfectly audible. I don't know what's wrong with other people. Yeah? You just check your settings or something. Okay. So basically, what I was talking about, in case of light radiations also consists of the small packets of energy, and those small packets, in case of light radiations, those are what we call as photons. Perfect. And my dear students, if light radiation consists of photons, if light radiation consists of these packets of energy, if I ask you, what is going to be the speed with which these photons are going to move? I'll say the speed with which, let me know in the chats, the speed with which photons are going to move. What is that speed? Absolutely, photons are going to move with the speed of light only. Because what is a photon? Light radiation consists of photons basically, right? So if I say light radiation is moving, that means these photons are moving with the speed equal to 3 into 10 raised per 8 meter per second, right? In vacuum. Perfect. This is something which I believe every one of you would have gotten till now. Okay. So quickly, a quick recap of what this Planck's quantum theory is all about. Then I'll talk about this a bit more in detail, right? So first of all, Planck's quantum theory, it supports the particle nature of light, number one. Number two, as per Planck's quantum theory, energy is transmitted in the form of small packets or small units, and you call those small units of energy as the quanta, right? Particularly in case of light radiations, these quantas are called as photons, right? A photon, it moves with the speed of light, which is 3 into 10 raised per 8 meter per second. I believe this is clear to everyone. Now, my dear students, try to understand. Imagine this is the source of light. Imagine this is the source of light. It is emitting light radiations. I'm assuming that the light radiations which this particular source is emitting, those light radiations are incident on me. Imagine that the light radiations which this particular source is emitting, right? These light radiations are, for example, incident on me. So I can say something like this. If light radiations are incident on me, light radiations, they consist of photons. So basically, these are the photons which are incident on me. These are the photons which are incident on me. And that photon which is incident on me, whatever energy that photon will be carrying, it is transmitting entire of its energy to me, basically. Right? As simple as that. Perfect, people? Right? Let's say over here we have got a source of light. It is continuously emitting light radiation. These light radiations are falling on me. So these are basically the photons which are falling on me. Every photon has got a particular value of energy, right? And whatever photon is incident on me, that photon is basically sharing, that photon is basically transmitting all its energy to me exactly, right? Basic thing. Now, my dear students, try to understand few more things. Try to understand few more things. See, if you ask me, what is the energy possessed by one photon? Energy possessed by a photon. Energy which one photon has, right, which I'm representing by E, is equal. Energy possessed by one photon is equal to h nu, my dear student. E is equal to h nu. This is something which I believe every one of you would be knowing. This E stands for energy possessed by one photon. It is directly proportional to the frequency of the light, right? It is directly proportional to frequency of the light. So, if energy is directly proportional to frequency of light, if I remove the proportionality sign, I'll be getting a constant h over here. And this particular h is something which you call as Planck's constant, right? You call this h as Planck's constant. Perfect. You call this particular h as Planck's constant. And what is the value of this Planck's constant exactly? If I ask you what is the value of this Planck's constant, my dear students, it's 6.6 into 10 raised power joules second. This is the value of your Planck's constant. Now, this is the energy possessed by one photon. Let's assume there are two photons. If there are two photons, energy possessed by two photons will be 2 times h nu. Energy possessed by 3 photons will be 3 times h nu. Energy possessed by n photons. Energy possessed by n number of photons will be equal to, energy possessed by n number of photons will be equal to, it will be equal to n times h nu. Perfect. Energy possessed by n photons will be simply equal to n times h nu. I believe this is clear to everyone. Perfect. The first result, that is the energy carried by one photon. This is the energy carried by n number of photons. Right, people? Now, as you all must be knowing, frequency of light. What exactly is it's going to be all about? What about this particular result? Frequency in terms of wavelength, what is it equal to? Quickly, frequency is equal to, frequency of the light is equal to c divided by lambda. This nu represents the frequency of light. This lambda represents the wavelength of the light. So, my dear students, the result which I wrote in the beginning, can I write the same result in a different format? I'll say E is equal to h nu, or I can say E is equal to hc divided by lambda. Similarly, E is equal to n times h nu. It can be written as nhc divided by lambda. It can be written as nhc divided by lambda. This is the energy possessed by one photon. This is the energy possessed by n number of photons. Right? Now, guys, be careful with certain things. Be careful with certain things. If I ask you, what is the SI unit of energy? Absolutely, you will say SI unit of energy is going to be joule. SI unit of energy is going to be joule. What are the other units of energy which we shall be using in this chapter? If I talk about the other units of energy which I shall be using over here in this chapter, that's going to be electron volt. Electron volt is one more unit of energy which I'll be using over here. And my dear students, do remember 1 electron volt, it is equal to 1.6 into 10 raised power minus 19 joules. Do remember this particular result as well. Joule is the SI unit of energy. One more unit of energy which I'll be using here, that is going to be electron volt. Do remember 1 electron volt is equal to 1.6 into 10 raised power minus 19 joules. Okay. Now, my dear students, what all things other than these you have to remember? See, my dear students, I told you energy possessed by one photon. Energy possessed by one photon is equal to either you'll be writing h nu or you'll be writing hc divided by lambda. H is the Planck's constant whose value is 6.6 into 10 raised power minus 34. C is the velocity of the light, 3 into 10 raised power 8. My dear students, let me tell you one simple thing over here. The combined value of H multiplied by C. The combined value of H multiplied by C. H multiplied by C. Its combined value you will be taking as 12400 electron volt angstroms. But do remember, when you take the combined value of H and C as 12400 electron volt angstrom, at that point of time, you have to take lambda in angstroms. At that point of time, you have to take lambda in angstroms. Similarly, my dear students, value of H multiplied by C can be written as 1240 electron volt nanometer. But when this particular value is taken, this particular value is taken only when lambda you will be taking exactly in nanometer. When you'll be taking the value of lambda in nanometers. Perfect. This is going to solve a lot of issues while you'll be doing the calculations and all, right? So now let's get to know what kind of questions can be asked from this Planck's quantum theory, right? And what all other things are there in the Planck's quantum theory, which we shall be discussing. Right, people? Yes? I hope all these things are clear till here. Look at these particular statements. According to the theory, energy is transmitted in the form of small packets or units. You call those units as quanta. In case of light energy, these packets are called as photons. Photon travels with the speed of light in vacuum. Energy possessed by a photon. Energy possessed by a photon is directly proportional to frequency of the light. Or when you remove the proportionality sign, a constant h will come, right? H is something which you call as Planck's constant, whose value is this much. Energy possessed by n photons is E is equal to n times h nu, right? All these things are discussed. All these things are discussed. SI unit of energy is joule. One more unit which we shall be frequently using, that's electron volt. 1 electron volt is equal to this much, right? The value of Hc you'll be taking as 12400 electron volt angstroms or 1240 electron volt nanometer. This value you'll only take when lambda is taken in angstroms. This value you'll only take when lambda is taken in nanometers, right? Perfect. So all these things I believe is clear to you. Let's try to solve one basic question so that you can understand where exactly these results, these basic results are used, right? And slowly you will see, we'll scale up the things, right? We'll make the things a bit complicated. See guys, calculate the energy of 100 photons. So we have got in total 100 photons, right? If the wavelength of light is 2000 angstroms, right? So we have got a light radiation. That light radiation consists of 100 photons. The wavelength of that light radiation is 2000 angstroms. What do we have to see? We have to see energy carried by 100 photons. You already know energy carried by n number of photons is equal to n times h nu, but here I'll be writing n times hc divided by lambda because I'm given with the value of wavelength of the light, right? Perfect. Now, my dear students, what all things are given to us? Wavelength of light is given to us in angstroms, so 2000 angstroms it's given, right? Number of photons, how many photons do we have in total? We have got 100 photons. So I'll simply say energy carried by 100 photons. Energy carried by 100 photons has to be equal to, it has to be equal to what? N. Number of photons, that's 100. Multiplied by H multiplied by C. Since lambda I'm taking in angstroms, so H multiplied by C, you'll be taking as 12400 electron volt angstrom divided by what? Divided by lambda. What is the value of lambda? Lambda is simply 2000 angstroms. So this angstrom gets cancelled out. You'll be getting the value exactly in electron volts, right? So this is the energy carried by 100 photons over here. This is the energy carried by 100 photons over here. So this double zero cancel, this zero cancel. So it is going to be, it's going to be 1240 divided by 2. The value comes out to be how much? This is 6, this is 2, this is 0. So 620 electron volts is the answer, right? This is the energy carried by 100 photons exactly, right? Now, my dear students, if they ask you to calculate the energy in joules, since you know the 620 electron volts, 1 electron volt is equal to 1.6 into 10 raised power minus 19. This is going to be the answer, particularly in joules, if they ask you. I believe it's clear to everyone, right? I believe it's clear to everyone. This is a very simple and basic question which I'm showing you. It is just the formula based one. Okay. Similarly, one more simple question I'm showing you. Have a look on this one. Have a look at this particular question. See exactly if you can solve this. A light source of wavelength, how much? Of wavelength 2000 angstroms, right? Emits energy. You have got a light source which is emitting radiation whose wavelength is this much, and energy possessed by energy is equal to 0.5 joules. The number of photons emitted from the source is. It's again a very simple question, correct? As per the question, you have got a light source which is emitting radiation whose wavelength is given, right? Perfect. Energy is equal to 0.5 joules. We have to see how many photons basically are emitted from the source exactly. So how do you do it? My dear students, imagine this is the light radiation which the source is emitting. This is the source, for example, it is emitting the light radiation. This light radiation consists of what? It consists of photons. Imagine this light radiation consists of n number of photons. Right? My dear students, this particular light radiation, its wavelength is given to me, right? Its wavelength is given to me as 2000 angstroms. Perfect. At the same time, energy possessed by this particular radiation. It's made up of n photons. So I'll say energy possessed by n photons. It is equal to how much? It is equal to 0.5 joules. We have to see exactly how many photons are there basically. How many photons are basically emitted by this particular source. How do you exactly do it? You know, energy possessed by n photons is equal to n times hc divided by lambda. Now, dear students, try to understand one simple thing. Energy is given to me as 0.5 joules. 0.5 joules is equal to n. H multiplied by c. I'll be taking the value as 12400 electron volt angstroms divided by lambda is given as how much? Lambda is given as 2000 angstroms. So can I say this angstrom gets cancelled? Absolutely. So this angstrom and this angstrom gets cancelled. Now, as you can see, don't commit this particular mistake. On left hand side, you have got joules. On right hand side, you have got electron volts. Now, you can only cross multiple things if the units on both the sides are same. But here it's joules, here it's electron volts. But you already know 1 electron volt is 1.6 into 10 raised power what? 1 electron volt is 1.6 into 10 raised power minus 19. Now the left hand side is also in joules. Now, my dear students, as you can see, you have got one equation which just contains one unknown, and that unknown is n. So n value you can easily calculate from here. Isn't it simple? Right? You have got one equation which just has got one variable n. So n value you can easily calculate from here. I believe these sort of basic equations you can easily do from now on. So, right? Now, my dear students, there is one more term here. That is power. That is the term power. How do you define the power of the source? How do you define the power of the source which is emitting radiations? Imagine we have got a source which is emitting light radiations. How do we define the power of that particular source? My dear students, it's a simple topic. How do you exactly define the power of the source? How do you exactly define the power of the source? Just a second. Okay. How do you exactly define the power of the source? Power, it is defined as energy emitted by the source divided by time taken. Power is equal to energy emitted by the source divided by time taken. Right? Energy emitted by the source divided by time taken. Now, my dear students, try to understand. I told you power of the source is equal to energy emitted by the source divided by time taken. Now, imagine the source is emitting the radiation which consists of n number of photons. So, energy possessed by the radiation will be equal to energy of n photons, which will be equal to n times h nu divided by t. Or you can write it like this, NHC divided by T, and this is lambda over here. Perfect. Now, my dear students, if I talk about power, whenever you have to calculate power exactly, power is going to be N divided by T, then it's going to be HC divided by lambda. This is the result by means of which you can easily calculate the power of the source. By means of which you'll be calculating the power of the source. Now, what is this N divided by T? What is N over here? N represents number of photons. T represents time. N by T. Combinedly, what do I call this N by T as? N by T represents the number of photons emitted per unit time. The number of photons emitted per unit time. Or this particular N by T, you'll be calling it as the rate of emission of photons. This N by T is something which you call as the rate of emission of photons. Sometimes a particular question is asked in which they'll ask you to calculate the rate of emission of photons. The rate of emission of photons. That means in that particular question, you have to calculate the value of N divided by T, right? And I believe all of you already know the SI unit of power. That's what? Right? That's what? Perfect. So, my dear students, quick recap of this particular slide. Power of the source is defined as energy emitted by the source divided by time taken, right? Energy is being emitted in the form of radiation, and energy possessed by that particular radiation, which consists of N photons, is equal to N times H nu divided by time. N times H nu can be written as C divided by lambda. So I got one particular result to calculate the power of the source, which is N by T Hc by lambda. This N by T combinedly is what we call as rate of emission of photons, right? Or you can say number of photons emitted in a unit time, right? Perfect. Now let's exactly get to know what kind of question can be asked from this. What kind of question can be asked from this power, right? It's a simple topic, right? Energy transmitted, energy emitted divided by time taken. That's it. N by T is something which you call as rate of emission of photon. My dear students, look at this particular question. See what this question exactly is all about. How many photons are emitted per second? How many photons are emitted per second? Number of photons emitted per second. Number of photons emitted per second. N by T. How many photons are emitted per second? By a 5 milliwatt laser operating at 620 nanometers. So we have got a laser which is emitting a power of 5 milliwatts, right? Which can be written as 5 multiplied by 10 raised power minus 3 watts, right? And this particular laser, it is operating at the wavelength of 620 nanometers. What do we have to calculate? You have got a laser. Which is delivering power of this much, right? The laser is operating at the wavelength of this much. And what are we supposed to calculate? We are supposed to calculate the number of photons emitted per second. So basically, we are supposed to calculate the rate of emission of photons. Can't you solve it? Isn't it a simple question now? I believe it's simple. Few minutes back only, I give you one result. Power is equal to N divided by T multiplied by Hc divided by lambda. Power is equal to N divided by T multiplied by Hc divided by lambda. So you have to calculate the value of N by T. So can I say N divided by T will be equal to T multiplied by lambda divided by H multiplied by C, right? This particular value. This is rate of emission of photons. This is something which I'm supposed to calculate. Now, how do I calculate it? My dear students, power is given to me. I'm taking power as per SI system. 5 into 10 raised power minus 3. Take lambda value. If power you are taking as per SI system, so lambda has to be taken in SI system as well. Lambda is 620 nanometers. So it can be written as 620 into 10 raised power minus 9 meters, right? Divided by H. H as per SI system is 6.6 into 10 raised power minus 34 joule second. Velocity C, velocity of light, which is 3 into 10 raised power 8 meter per second. So all the parameters I have taken as per SI system. It is now the matter of calculation. You will be getting the number of photons emitted per second, which is something which you will be calling as the rate of emission of photons. Rate of emission of photons. So in this particular question, rate of emission of photons were asked, and you exactly calculated the rate of emission of photons, right? I believe calculation part you can do on your own. Is this particular question clear to you? Let me know once in the chats. Quickly, people. Everyone, quickly. Quickly, my dear students. Everyone in the chats. Everyone in the chats. Is this particular question clear? I took power as per SI system. That's why lambda I had to take as per SI system. H as per SI system. C as per SI system. Right? So at the end, you'll be getting the number of photons emitted per second, which is something which you call as rate of emission of photons. Now, my dear students, one more application of this Planck's quantum theory. What is that? One more application of this Planck's quantum theory. What is that? That is photodissociation. That is photodissociation. How do you exactly define photodissociation? How do you define it? So first of all, let me tell you this photodissociation, it is defined as breaking of chemical bond using light energy. This is something important, right? A particular type of question will be framed on photodissociation. Let's try to understand the concept first. Then I'll make you understand what it exactly means. Okay? Have a look, people. Have a look. Let's say I've got a bond between A and B. Let's say there's a chemical bond between A and B. Okay? If I first of all ask you what is a bond? What is a bond? Bond is just the force of attraction which is holding these atoms together. A chemical bond, it is just the force of attraction which is holding these atoms together. Perfect. My dear students, if I ask you, what if I break this particular bond? What if I break this particular bond? How do I break this particular bond? Since a bond is a force of attraction between these atoms. It's a force of attraction between these atoms. Now, my dear students, I have to break this force of attraction. In order to break the force of attraction, what do I need to do? I need to supply some energy. I need to supply some energy towards this bond. Then only this force of attraction will be broken down. The energy which I'm supplying, imagine that I'm supplying this energy in the form of light radiations. Imagine that I'm supplying this energy in the form of light radiation. In the form of light radiation. So, what is going to happen? A bond will get broken down. A bond will get broken down. Breaking of a chemical bond with the help of light energy. Breaking of a chemical bond with the help of light energy is something which you call as photodissociation. Whenever you break a bond, whenever you break a force of attraction between the atoms with the help of light radiation, you call this particular phenomenon as the photodissociation. Now, people, what all things we have to understand from here? What all things we have to understand from here? See. My dear students, imagine a bond is between A and B, right? There's a bond between A and B. For example, I'm telling you the bond energy of this particular bond, it is X kilojoules per mole. It is X kilojoules per mole. I'm telling you the bond energy over here is equal to X kilojoules per mole. What does it mean? What does it mean? It means that in order to break 1 mole of bonds, in order to break 1 mole of bonds of this particular type, how much energy am I supplying? X kilojoules of energy I'm supplying, right? So from this particular data, from this particular thing, what I got to know? I got to know that in order to break 1 mole of bonds, in order to break 1 mole of bonds of the type AB, how much energy is required? I'll say X kilojoules of energy is required. This much energy is required. Now, my dear students, imagine that this much amount of energy, which is required to break 1 mole of bonds, Imagine this much amount of energy I'm supplying in the form of light. Imagine this much amount of energy I'm supplying in the form of light, in the form of H nu. So can I say, if I supply this much of amount in the form of light radiation, can I say the bond will get broken down? Absolutely. The bond will get broken down. Now, my dear students, try to understand one simple thing which I'm going to tell you now. See, try to understand. Let me erase this part here. See, I told you in order to break 1 mole of bonds, this much energy is required. Now tell me one thing. 1 mole of bonds exactly contains how many bonds? It contains Na bonds, Avogadro's number of bonds. So can I say in order to break Na bonds, X kilojoules of energy is required? So what if one bond is to be broken down? What if one bond is to be broken down? Can I say in order to break Na bonds, this much energy is required? So in order to break one bond, how much energy is required? X divided by Na kilojoules. So this much amount of energy is required to break one particular bond. And my dear students, imagine that this much amount of energy I'm supplying in the form of what? In the form of light radiation. Whose energy is h nu. So this much energy I'm supplying in the form of h nu. Perfect. Or instead of h nu, you can write hc divided by lambda. So my dear students, I'm getting an equation over here. And equation is like this. X, that is the bond energy of the bond, divided by Na. Now this is in kilojoules, right? So let's make it in joules. So 10 raised power 3 is equal to Hc divided by lambda. From this particular equation, anything can be asked, right? Or if you write the same equation in the generalized form, this X was your bond energy. So bond energy divided by Avogadro's number multiplied by 10 raised power 3. The left hand side is in joules and right hand side I'm assuming also in joules. Perfect. Right hand side I'm assuming also in joules. So from this particular equation, a particular type of question can be asked. I hope you got to know how I made this particular equation. I hope you got to know it. Let me know once in the chats if it is clear. Let me know once in the chats if it's clear, people. Let me know once in the chats quickly. Yeah? Is the concept clear? Then only I can move ahead. Right? Perfect. Look at this particular question. From this question, you can easily solve now. If you got the concept, this question you can easily solve. The question is calculate the wavelength of a photon. Calculate wavelength of a photon required to break Cl single bond Cl. Required to break Cl single bond Cl. If the bond energy of Cl single bond Cl is 1.2 kilojoules per mole. Can't you solve it now? Isn't it simple? My dear students, you have got a bond between two chlorine atoms. This is the bond. Well, bond energy value is given to us. How much? Bond energy value is given to us as 1.2 kilojoules per mole. Right? Now, my dear students, there is a photon which is incident on it. Right? Perfect. What do we have to calculate? We have to calculate wavelength of this light, wavelength of this photon. We have to calculate wavelength of this photon, which is enough to break this particular bond. How do you do it now? Say, the same procedure. I'll say, in order to break Na bonds, between two chlorine atoms, how much energy is required? 1.2 into 10 raised power 3 joules of energy is required. That means in order to break one bond between two chlorine atoms, how much energy is required? I'll say 1.2 into 10 raised power 3 divided by Na. So these many joules of energy is required to break one Cl single bond Cl. Right? Imagine this much energy you are supplying in the form of photon. Energy carried by that photon is h nu, or you can say it is hc divided by lambda. Right? hc divided by lambda. Now, my dear students, you just have to equate these two. That's all. The question is done and dusted. The equation will be like this: 1.2 into 10 raised power 3 divided by Avogadro's number, approximately 6 into 10 raised power 23. The left hand side, I'm taking in joules. So right hand side, you also have to take in joules only, right? Because I've multiplied with 10 raised power 3 over here. So H value is 6.6 into 10 raised power minus 34, right? Joules second. C, velocity with which the photon moves, which is 3 into 10 raised power 8 meter per second divided by lambda. Look at this particular equation. Can I say I got one equation which just contains one variable, that's lambda. So you can calculate lambda easily from here, right? And my dear students, the point is this lambda. What will be the units of lambda while after calculation is done? Units of lambda after this calculation is done. Since this term you have taken in joules, SI system, SI system, so lambda value will come in meters as per SI system only, right? Is that clear, people? So I believe these sort of questions you can easily solve, right? Okay, look at this particular question. One more similar type of question, and I believe you can solve it. I believe you can solve this question as well. Look at the question, people. Calculate the number of photons. Calculate the number of photons of light. Wavelength is given. Required to dissociate 1 mole of Cl2Cl2 into chlorine atoms. If the bond energy of Cl bond is 1.2 kilojoules per mole. Calculate the number of photons required to dissociate 1 mole of Cl2. So right now you do not have to dissociate one bond. You have to dissociate 1 mole of bonds, right? You have to dissociate 1 mole of bonds. See guys, as per the question, bond energy of Cl2 is 1.2 kilojoules per mole. Try to understand what I'm going to say. Now, as per this particular data, I can say in order to break 1 mole of bonds between two chlorine atoms, in order to break 1 mole of bonds, how much energy has to be supplied? I'll say 1.2 kilojoules. Write it in joules. So 1.2 into 10 raised power 3 joules. So this much amount of energy is required to break 1 mole of bonds. And as per the question, I have to break 1 mole of bonds only. I do not have to break one bond. I have to break 1 mole of bonds, right? Assume that in order to break 1 mole of bonds, n photons are required. Assume that in order to break 1 mole of bonds, n photons are required. Now, what is the energy carried by those n photons? That's going to be NHC divided by lambda. That's going to be NHC divided by lambda. I just have to equate it. The question is done and dusted. Have a look. It's going to be 1.2 into 10 raised power 3. Left hand side is in joules. So right hand side also has to be in joules. Perfect. N represents number of photons, which I have to calculate. H value, that is 6.6 into 10 raised power minus 34 as per SI system. C value is 3 multiplied by 10 raised power 8 meter per second as per SI system. Lambda value is equal to 2000 angstroms. But you know 1 angstrom is 10 raised power minus 10 meters. Why am I using meters? Because I have taken every parameter as per SI system, right? That's how your right hand side also comes in joules only. If I take all the parameters as per SI system, right? Now again, one equation, one unknown, right? What is the unknown value here? Unknown is N. N you can easily calculate. So N gives you the number of photons. N gives you the number of photons which are required to break 1 mole of bonds over here, right? N represents number of photons which have got wavelength of 2000 angstroms, which are required to break 1 mole of bonds. Let me know once in the chats if it is super clear to everyone. Quickly, guys. Let me know once in the chats quickly if it is super clear to everyone. Yeah? I mean, will you be able to solve these sort of questions? I have no idea what exactly the answer. It is just the calculation, guys. Do the calculation part. Your job. I'm not going to do that. What are you going to do then? I'll teach also. I'll do the calculation also. I'll write on the screen also. Right? You're just watching and listening to the lecture. Yeah? Perfect. Chalo. Let's get going and let's see one more important topic. What is that? That is photoelectric effect. Photoelectric effect. My dear students, what photoelectric effect is all about? I believe you would have studied this in physics as well, right? So let's get into the details of the photoelectric effect. Let's see what all things are here. See, there are few terms basically which we need to know related to photoelectric effect. One is photoelectron, one is photoelectric current, one is maximum kinetic energy of the photoelectron, one is stopping potential, one is intensity, frequency, variation of kinetic energy with something. It's a detailed topic, right? It's a detailed topic. So let's get to know from the basics itself what this photoelectric effect is all about. For example, people, imagine that I'm taking a tube over here. Imagine that this is a tube over here. Okay. Imagine that it's a discharge tube over here, right? There is vacuum. There is nothing inside this glass tube. There is nothing inside this glass tube. Now over here, I'm going to keep a plate, a metal plate. This is a metal plate over here. This is something which I call as photosensitive metal plate. So this plate is made up of a photosensitive metal. Now what is a photosensitive metal first of all? What is the photosensitive metal? How do we define it? What is the property of the photosensitive metal? Imagine that this plate, it is the photosensitive metal plate. Now, my dear students, if some light radiations are incident on this plate, what will happen? If light radiations are incident on this plate, from the surface of the plate, electrons will be emitted. Electrons will be knocked out. Electrons will be knocked out, right? So that particular metal, from the surface of which electrons are knocked out when light radiations are incident on it, you call that plate as the photosensitive plate. So what is a photosensitive plate? It is the plate from which electrons are knocked out when light radiations fall on it. That plate is something which you call as photosensitive plate, right? Now, my dear students, over here, I've got one more plate. Okay, I've got one more plate. Now, what I'll be exactly doing, I'll be connecting these plates with a battery, for example. I'll be connecting these plates with a battery, right? This is negative, this is positive, this is negative, this is positive. Perfect. Now, first of all, this is the negative terminal of the battery. This is the positive terminal of the battery, right? So that negative terminal, which is attached to this particular plate, right? So this particular plate will be carrying negative and this particular plate will be carrying positive. Okay. Now, my dear students, what is going to happen? Imagine some light radiations are incident on this metal plate, right? When light radiations are incident on this metal plate, what will happen? From the surface of the metal plate, electrons are going to be emitted. Electrons are knocked out, basically. Electrons are knocked out from the surface of the metal. This phenomenon in which the electrons are knocked out from the surface of the metal when light radiation falls on it. This particular phenomenon is what you call as photoelectric effect. This particular phenomenon is what you call as photoelectric effect, right? And my dear students, one more thing. This particular plate, what do you call this as? You call this as emission plate. You call this plate as the emission plate. And this particular plate, you call this as collector plate. Why do we call this as collector plate? It's simple. The electrons which are coming out from the surface of the metal, now these electrons will be dragged by this particular plate because this particular plate carries a positive charge, is going to attract those electrons towards itself. So these electrons will start moving in a particular direction. The electrons which are coming out from the surface of this particular metal, those electrons are now moving towards the collector plate, my dear student. So if I ask you one thing, is there only the movement of electrons, or I'll say the electrons are moving in a particular direction? First of all, the electrons which are coming out from the surface of the metal, these electrons are what you call as photoelectrons. These electrons are what you call as photoelectrons. Now, once these photoelectrons are coming out from the surface of the metal, these photoelectrons will start moving towards the collector plate, right? Due to which these photoelectrons are moving in a particular direction. And whenever charge moves in a particular direction, it leads to the generation of current. And that current which is generated over here, that current is something which you call as photocurrent. That current is something which you call as photocurrent. And this particular process, my dear students, in which the electrons are taken out from the surface of the metal, when light radiation of some frequency falls on it, this particular phenomenon is what you call as photoelectric effect, right? So in case of photoelectric effect, what happens basically? Electrons are knocked out from the surface, and those electrons are what you call as photoelectrons, which move towards the positively charged plate, which is what you call as collector plate, right? So if the electrons are moving in a particular direction, it leads to the generation of current, and that particular current which gets generated due to this particular phenomenon. That's what you call as photoelectric current or photocurrent. Is this particular point clear to you? Is this point clear to you, people? From where the light comes? We are sending the light here. We are sending the light from outside, right? From outside source. There is some light source which is present over here, which is sending light towards this particular plate, right? Nothing else. Read all these statements once. Read all these particular statements once. My dear students, this photoelectric effect, it supports the particle nature of light. Point number one. It supports the particle nature of light. Number one. Number two. When light is incident on a certain matter, electrons are emitted. These electrons are what we call as photoelectrons. The current which flows due to the motion of these photoelectrons is called as photoelectric current, or you call this as photocurrent, and this phenomenon over here is what you call as photoelectric effect, right? Now let's go a bit more into the details of it. Try to understand, my dear students, what exactly I'm going to say. Imagine this is a metal surface of some photosensitive metal. Imagine this is the surface of some photosensitive metal, right? Let's say that photosensitive metal is M. Perfect. My dear students, in this metallic plate, what do we see? In this metallic plate, you will see a lot of M positive ions, which are what you call as kernels, basically, right? You will see a lot of M positive ions, and in between you see millions of electrons, right? In between them you see millions of these electrons. This is the surface of the metal plate which I'm showing. So on the metal plate, what do you see? Inside the metal plate, what do you see? You see these metal ions and the large number of electrons over here. Okay. Now, for example, if I focus on one particular electron, this is the metal surface which I'm focusing on. And I'm focusing, for example, on this particular electron. Since electron carries the negative charge, so this M positive will be attracting the electron towards itself. Even this particular M positive will be attracting this electron towards itself. So tell me one thing, whether this particular electron, whether it is present in free state or bound state. Whether this particular electron, it is present in free state or bounded state. This electron is bounded, basically. On the surface of the metal, this particular electron, it's bounded, right? Yes. Now tell me one thing. Since this electron is being attracted by all these M positive ions. Perfect. Now, my dear students, tell me one thing. Since this M positive is attracting this, even this M positive is attracting this. If I want this electron to be taken out, what should I do? I have to break this force of attraction between the electron and M positives. How do I break the force of attraction? I have to send some radiation. I have to send some energy. I have to make sure some energy falls on the surface so that this force of attraction breaks. And this energy which I'm sending this energy in the form of light. Perfect. So, my dear students, try to understand one thing. The light radiation which you are sending, it is breaking the force of attraction between the electron and the metal ions. Then only the electron is coming out. Let me tell you, the minimum energy which is to be needed, the minimum energy which is needed to take the electron out from the surface of the metal, the minimum energy which is needed to take the electron out from the surface of the metal, that minimum energy needed is something which you call as work function or threshold energy. So there's a term called as work function. There's a term called as work function. There's a term called as work function, which is denoted by phi naught. So what is work function? How do you explain this work function to me? The minimum amount of energy which is required to take the electron out from the surface of the photosensitive metal, right? And that minimum amount of energy which is required, which I'm supplying in the form of photon, right? That minimum energy required is something which you call as work function, right? If I ask you, work function, what should be its value? What is work function? It is the minimum amount of energy which is required to knock out the electron from the surface. And that minimum amount of energy you are supplying in the form of photon, right? Can I say it will be equal to h nu naught? It will be equal to h nu naught, right? It will be equal to h nu naught, or nu is equal to c by lambda, or you can write it as h c divided by lambda naught. Oh, there are a lot of terms, a lot of new terms are coming here. What a lot of new terms are here? Number one, this is your work function, or you call it as a threshold energy. This nu naught, it is something which you call as threshold frequency. This is called as threshold frequency. This lambda naught is something which you call as threshold wavelength. This is called as threshold wavelength, right? Now, my dear students, if I ask you, try to define this threshold frequency. Try to define this threshold frequency. Can I say threshold frequency? It is basically the minimum frequency, the minimum frequency carried by the photon, the minimum frequency which the photon has, such that that photon is taking the electron out, right? That minimum frequency required to take the electron out, that is something which you call as threshold frequency, right? That's something which you call as threshold frequency. The minimum frequency which is required to take the electron out, that's called as threshold frequency. My dear students, if this is minimum, means this has to be maximum. So what is lambda naught? Should I define lambda naught as minimum wavelength or maximum wavelength? If this is minimum, that means this automatically becomes maximum. So what is lambda naught? It is the maximum wavelength of the photon. It is the maximum wavelength of the photon, right? Which is just taking the electron out. So I got three terminologies over here. Threshold energy, which is what you call as work function. How do you define it? The minimum energy which is required to take the electron out from the surface of the matter. Threshold energy or work function. Threshold frequency is the minimum frequency which is required, right? Minimum frequency which is required to take the electron out. Lambda naught is the maximum wavelength which is required to take the electron out from the surface of the matter. So three new terms here. Yeah? Right, people? Is it clear? So let's try to have a look on these terminologies which I have discussed with you. I did not discuss them in detail yet. We have to discuss them in detail. I'm just giving you the idea of the things. Okay? So work function, which is what you call as threshold energy. How do you define it exactly? How do you define it? It is basically the minimum energy which is required. Minimum energy which is required to eject, to take the electron out from the surface of the matter. Right? And you represent this with the help of phi naught, which is either equal to h nu naught, or you can call it as hc divided by lambda. Right? Now, every metal has got a particular value of its threshold. Every metal, whatever metal surface you take, every metal surface has got a particular value of its threshold energy, right? Some metals will have more threshold energy because there will be more force of attraction between the electron and the ions. Some metals will have less threshold energy because there will be less force of attraction between the electrons and the ions. So every metal has got a particular value of the threshold energy, particular value of work function. So work function, it is basically a characteristic of what? It is the characteristic of metal basically. Work function, on what parameters it depends on? It depends on the amount of force of attraction between the electron and the metal ions. Perfect. More the attraction, more the energy needed, more the work function. Yeah? I believe it's clear. This particular thing. What is this particular thing? Threshold frequency, which is something we defined a few minutes back only. Threshold frequency, it is the minimum frequency. It is the minimum frequency which the photon has just to take the electron out. Right? Right, guys? The minimum frequency required to eject an electron out of the surface of the metal is something which you call as threshold frequency. Right? And this threshold frequency, it is represented by mu naught, which is equal to c divided by lambda naught basically. Which is equal to c divided by lambda naught. I believe this particular point is also clear. I believe this particular point is also clear. Now, similarly, guys, what about threshold wavelength? Threshold energy was minimum energy. Threshold frequency was minimum frequency. Threshold wavelength will be maximum wavelength. The maximum wavelength, the maximum wavelength, the maximum wavelength required to eject an electron from the surface of the metal is something which you call as threshold wavelength, right? If this is threshold frequency, it is the minimum frequency. If this is minimum frequency, this has to be maximum wavelength, right? So lambda naught here is the threshold wavelength over here. Perfect. So I believe all these things are till here clear to you. Now, my dear students, let's try to understand and analyze certain mathematics behind it. See, guys, try to understand. For example, this is the surface of the metal. Imagine that this is the surface of the metal, right? This is the surface of the metal M. Now, on the surface, what do you observe? You'll be observing M positives and millions of electrons. M positives and millions of electrons. M positives and millions of electrons you'll observe here, right? Millions of electrons you'll observe here. So, my dear students, particularly if I talk about this electron, right? This electron is attracted by this M positive as well as this M positive. Just to make you understand, this particular electron, it is attracted by this M positive as well as this M positive. Now, I want to take this electron out. If I want to take this electron out, what do I have to do? I have to break this force of attraction. Absolutely, I have to break this force of attraction, right? Let's assume that minimum. Let's assume that minimum 50 joules of energy. Let's assume that minimum 50 joules of energy is required to take this electron out. And that minimum energy which is required to take the electron out from the surface of the metal, that's what you call as work function. So this 50 joules over here, let's say this is the work function of the metal. This is the work function of the metal. Now tell me one thing. Imagine that this is the photon which is going to be incident on this particular surface. Let's say this photon carries the energy of 80 joules. This photon carries the energy of 80 joules. So this 80 joules I'll be calling as incident energy. I'll be calling this as incident energy. So how much is the incident energy carried by the photon? 80 joules. Minimum how much is required to take the electron out? 50 joules. So how much energy I'm sending? I'm sending 80 joules to the surface. Out of 80 joules, 50 joules is required. 50 joules is required to set free this electron, to take the electron out. What about the remaining energy? Remaining energy is 30 joules. This 30 joules is imparted by the electron in the form of its kinetic energy, right? This is basically going to be this 30 joules. It will be imparted to the electron in the form of its what? In the form of its kinetic energy. So basically, out of 80 joules, 50 joules are required to take the electron out. Now the electron which got out, it will be moving on the cost of this 30 joules, on the cost of this particular 30 joules, right? So can I say something like this? Can I say something like this? What was this 80 joules? This was incident energy. What was this 50 joules? It was work function. What is this 30 joules? This 30 joules is imparted to electron in the form of its kinetic energy. So this is your kinetic energy max of the electron. This is the equation, which is something you call as photoelectric equation. This equation is something which you call as photoelectric equation. So this is your photoelectric equation basically. This is your photoelectric equation. Incident energy is equal to work function plus what? Plus maximum kinetic energy possessed by the electron after the emission. Okay. Now, my dear students, you can write different formats of it. Incident energy, I'm giving in the form of photon, so this h nu. Work function is h nu naught. You can write it as such, Ke max, maximum kinetic energy, which is possessed by the emitted electron. Right? Instead of h nu, you can write hc divided by lambda is equal. Instead of this, you can write hc divided by lambda naught plus kinetic energy max. Right? Maximum kinetic energy possessed by the photoelectron. Perfect. Right? Yeah. And my dear students, at the same time, this hc divided by lambda, it can be written like this as well. hc divided by lambda naught. Maximum kinetic energy possessed by the photoelectron will be half of half of mass of electron and V max of an electron, a square. It can be written like this as well. So these are different formats of this particular equation, right? These are different formats of this particular equation. So in nutshell, if I need to summarize it, how would I summarize it? I don't understand. The energy which is incident on the metal surface, it is used in two parts. The energy which is incident on the metal surface, it's divided in two parts. Number one, some part of the incident energy is used to eject the electrons out of the surface of the metal in the form of work function, right? And the remaining incident energy is used to provide the kinetic energy of the ejected electrons, right? Yes? Right, people? So, due to this particular scenario, what did we get? We got one equation. Equation was your incident energy is equal to work function plus maximum kinetic energy possessed by the emitted electron, right? These are the different formats of this particular equation, right? All these formats I've already shown you. Now, my dear students, let's have a look on a few more things. Let's have a look on a few more things. Imagine that this is the photon which is incident on the surface. This photon carries the energy h nu. This photon carries the energy h nu. This photon is incident on the surface. Perfect. Right? Imagine work function. Work function here is something, let's say. Let's say work function here is 50 joules. Let's say work function here is 50 joules. Tell me one simple thing. What is this 50 joules? It is the minimum energy which is required to take the electron out. It is the minimum energy required to take the electron out. Imagine that h nu value is equal to, for example, 80 joules. Imagine that energy possessed by electron. Sorry, energy possessed by the photon, which is h nu. Imagine that it is equal to 80 joules. Out of 80 joules, how much is used to take the electron out? 50 joules. Remaining is 30 joules. Those 30 joules are imparted to the electron. Those 30 joules electron is going to get in the form of its maximum kinetic energy after the emission. You know it. Now tell me one thing. If I increase the frequency of the incident light, that means on increasing the frequency of the incident light, energy of the photon is increasing. Energy of the incident light is increasing. If energy of incident light is increasing, imagine we are increasing the energy to 100 joules. Now the incident energy is 100 joules, right? On increasing the energy, will anything happen to work function? Work function is still the same, 50 joules. Work function is still the same. I'm increasing the frequency of the incident light. I'm increasing the energy of the incident light. By increasing the energy of the incident light, nothing will happen to work function, right? It is a characteristic of the metal. Where you will see the chains? Initially, the kinetic energy was the kinetic energy of the emitted electron. That was 30 joules. But if this is made 100 joules, will the kinetic energy of photoelectron be 30 joules now or 50 joules? That will be 50 joules. 100 minus this value, that will be 50 joules. So, in short, can I say something like this? On increasing the frequency of the incident light, kinetic energy of the photoelectron, does it increase or decrease? It increases. Kinetic energy of the photoelectron, it increases. Okay? Can I say something like that? Absolutely. Now let's try to make a graph between kinetic energy and frequency of the incident light. This is kinetic energy of the photoelectron. This is frequency of the incident light. Now what will be the nature of the graph? Try to understand. See guys, from this particular equation, you can say kinetic energy maximum is equal to h nu minus h nu naught. Agreed? We have to make a curve between this particular term and a nu over here. Now kinetic energy you are plotting along y-axis. This frequency of the incident light you are plotting along x-axis. This h is going to be your m. This particular whole term is going to be your c. The sign here is minus. This is equal to y is equal to mx minus c. Y is equal to mx minus c. It's going to be a straight line. Y is equal to mx minus c. It's going to be a straight line. But this straight line won't be passing through the origin. It will start down the origin because of this negative intercept. right? Because the sign of intercept is minus. So it is going to be a straight line, but this straight line won't be passing through the origin. It will start down the origin. This was the origin here, right? The distance from the origin to the point from where the curve starts. The distance from the origin to the point from where the curve starts. That means this particular distance I'm talking about. What do we call this distance as? This is called as intercept. Intercept is C, and C value over here is h nu naught. So this term is h nu naught over here, right? If I ask you the slope of this curve, slope means m, and m value here is h. So slope of this particular curve is simply h, right? Agreed? Agreed, guys? So what is happening basically? On increasing the frequency of the incident light, the kinetic energy of the photoelectron, that is increasing. The speed with which the photoelectron moves, that increases. I believe it's clear to everyone. Now, my dear students, there are few things. There are few things which you need to know. Let me tell you, one photon is enough to knock out one electron. One photon is enough to knock out one electron. Two photons cannot eject one electron. Two photons cannot knock out one electron. One photon will only knock out one electron. That is why this photoelectric effect is also called as one photon. This is also called as one photon, one electron emission. This is also called as one photon, one electron emission. What it means, why this is important, why this is important. Try to understand. You might think in this way. You might think in this way. Let's say this is the electron. In order to take the electron out, you have to give around 50 joules, right? Now you must be thinking, let's make sure that two photons are incident on this, one carrying 25 joules, one more carrying 25 joules. You might be thinking 25 plus 25 is 50, and that 50 is enough to take this electron out. But my dear students, this is not the case here. One photon will take out one electron. Two photons cannot take two electrons out. One photon, one electron. One electron is going to take one photon. Sorry, one photon is going to take one electron out. Right? Two photons can never take one particular electron out. Okay? Point number one. Point number one. Point number one. Point number two. My dear students, when a photon of a particular frequency strikes the surface of the metal, when a photon of a particular frequency strikes the surface of the metal, the process is all instantaneous. As soon as the photon strikes the metal surface, at that time itself, electron is emitted. There is no time lag. There is no time lag. There is no time lag between the striking of photon and the emission of photoelectron. There will be no time lag. It's not like that the electron is going to strike the metal surface, then it will take some 5 seconds, then the electron will come out, right? It's not like that photon will strike the surface, then it will take 5-10 minutes, and then slowly it will go out. No, it's not that. There's no time lag in between. There's no time lag in between. This is one more important point. Why these points are important? You will get their significance in some time. In some time, you will get their significance. Okay? Now, we will try to understand few more things. Try to understand few more things. If you ask me exactly, what are the conditions which must be satisfied for the photoelectric effect to happen? What are the conditions which should be satisfied? My dear students, the condition is very simple. The condition is very simple. Since you know one electron is enough to take one photon is enough to take electron out, right? Do remember, incident energy has to be greater or equal to the work function. Incident energy has to be greater or equal to the work function. This is the condition which should be satisfied. Then only the electron can be knocked out from the surface of the metal, right? This is the condition, simple condition. The incident energy should be greater or equal to the work function. Number one. Number two, you can make one more condition. Incident energy is basically h nu. So h nu should be greater or equal to h nu naught. What does that mean? That means nu should be greater or equal to nu naught. What is this nu? This is the frequency of the incident light. Frequency of the incident light should be greater or equal to threshold frequency. This is one more condition. Either you talk in terms of energy Or you can talk in terms of this particular frequency as well. Frequency of the incident light should be greater or equal to the threshold frequency. Then only the electron will be knocked out. Now one more thing. Frequency is C by lambda. So C by lambda should be greater or equal to C by lambda naught. Right? This lambda naught is C by lambda naught. So CC gets cancelled. If you take the reciprocal, you can say lambda should be less or equal to lambda naught. This is one more condition. This is one more condition. This is the wavelength of the incident light. This is the threshold wavelength. Wavelength of the incident light should be less or equal to threshold wavelength. Then only photoelectric effect will happen. Then only electron will be knocked out. Then only electron will be knocked out. Right? Is this clear, people? Clear, guys? Is this clear? Let me know once in the chats quickly. Perfect. So if incident energy is less than work function, or incident frequency is less than threshold frequency, no photoelectrons will be emitted. No photoelectric will be observed. But if incident energy is greater than work function, or if incident frequency is greater than threshold frequency, photoelectric effect will be observed. So these are the conditions which you have to remember, either in this format or in this format or in this particular format, right? These are the three formats which we have. Now, my dear students, if this is clear, can you answer me this question? The work functions of some metals are listed below. The number of metals which will show photoelectric effect when light of 300 nanometers falls on the metal. So the light which is going to fall on the metal, it has got the wavelength of 300 nanometers. So that means, what is the energy of the incident light? It is Hc divided by lambda. Hc I'll be taking as 1240 electron volt nanometer divided by lambda is going to be 300 nanometer, right? So nanometer cancel. So 0000 is going to be 4.1 electron volt. This is the energy of the incident light. This is the energy of incident photon. This is the energy of incident photon. Now you have got lithium. You have got lithium, right? Now, my dear students, imagine if the photon carrying this much of energy, if that is incident on lithium, will photoelectric effect happen? Will it happen? Absolutely it will, because threshold here is less. Minimum this is required, but you're supplying more, right? So here, photoelectric effect will be observed. Here again it's less, it will be observed. Here again it's less, it is observed. Here again it's less, observed. Not here, not here, not here. This was the question asked in your JEE Mains 2 years back. In how many metals photoelectric effect will be observed? So there are 4 metals wherein we can see the photoelectric effect. Yes? Perfect, guys? I believe it's clear. Look at one more question. See what the question is. If the work function of a metal is something, its threshold wavelength and maximum kinetic energy. Threshold wavelength and maximum kinetic energy emitted when the radiation of 300 nanometers strikes the metal. So basically what is happening? Let me show it to you. Let me show you the exact scenario. This is the metal surface. Work function of this surface of this metal is 3.1 electron volts, right? Now you have got a light radiation which is incident on the surface. Perfect. Wavelength of the light which is incident on the surface, that is 300 nanometer, right? That is 300 nanometer. Now what is happening? When this light is falling on the surface, electron is emitted. Electron will be emitted with some kinetic energy. We have to first of all calculate that maximum kinetic energy which the electron has. Right? And at the same time, what do we have to calculate? We have to calculate the threshold wavelength as well. Lambda naught also is to be calculated. So 2 things we have to calculate. I believe you can do it easily. My dear students, let's have a look first of all on threshold wavelength. You know your lambda naught work function. It's equal to h nu naught, right? Or you can say it's equal to hc divided by lambda naught. So can't you calculate lambda naught from here? This hc divided by phi naught, right? hc divided by phi naught. You can calculate lambda naught. My dear students, hc value you can take as 12400 electron volt in nanometer, because everywhere it's nanometer. Phi naught is 3.1 electron volts. Electron volt cancel. Solve it. Get the value of lambda naught, which is your threshold wavelength. So you calculate your threshold wavelength from here. Now threshold wavelength is calculated. Now use the photoelectric equation. Photoelectric equation says that incident energy is equal to phi naught plus maximum kinetic energy possessed by the photoelectron. What do we have to calculate? We have to calculate the maximum kinetic energy, right, of the photoelectron emitted. EI is just going to be hc divided by lambda. This is going to be hc divided by lambda naught plus kinetic energy maximum. So from here, you can calculate maximum kinetic energy. What is it going to be? hc you will take common. It's going to be 1 divided by lambda minus 1 divided by lambda naught. Or you can say lambda naught minus lambda. Or you can keep it as such. The choice is all yours. Right? Now people, try to understand. Lambda value is given to us. 300 nanometers. Right? Lambda naught we have calculated from here. In nanometers. hc value will be 1240 electron volt nanometer. When you put all the terms in this particular expression, you'll be getting the answer in terms of electron volts here. So that's going to give you the maximum kinetic energy of the emitted electron. Yes? Right, people? Is it clear to you? Let me know once in the chats quickly. Is it clear? I believe it's clear to you. Right? Now we're talking about few more things. There is a term called as, or just a second. There is a term called as stopping potential. What is stopping potential all about? This one more term. Stopping potential. My dear students, it is defined as the reverse potential, which is applied to stop the most energetic photoelectron from reaching the anode. What does it mean? Let's have a look, people. See, this was your anode and this was your cathode basically. Perfect. Now light radiation is coming, taking the electron out. Perfect. The electron, it is coming towards anode. Now, my dear students, if I change the polarity of this particular plate, this plate carries positive charge. It is at positive potential. If I change the potential of this anode, changing the potential of this anode means, since it was positive, if I make it negative, can I say the electron which was supposed to come in this direction, that electron will experience the repulsions from this negatively charged plate, right? That electron will experience some repulsions from the negatively charged plate. My dear students, if I keep on increasing the negative potential of this plate, what will happen? The electron which was supposed to come, it will experience more repulsions. I'm continuously increasing the reverse potential of this plate. I'm continuously increasing the negative potential of this plate. What is going to happen? Can I say there'll be a time at which the most energetic photon will stop? That will not reach this anode. That reverse voltage, that reverse potential at which the most energetic photon stops, highly energetic photon stops, that reverse voltage is something which you call a stopping potential. So what is stopping potential? Is it the normal voltage or reverse voltage? You are giving the reverse voltage. See, this was your positively charged plate, but this was at positive potential. Now you are changing its polarity, you are changing its potential, you are making it negative potential, right? Perfect. So you are reversing its polarity. right? You are reversing its polarity. How you'll be reversing its polarity? Maybe you'll be connecting these plates with some other battery, right? Maybe you'll be connecting these plates with some other external battery, but in the reverse format, not in this particular format, in the reverse format. And that battery, its voltage you'll keep on increasing. When you keep on increasing the voltage of that external battery, which is connected to these plates in the reverse form, what will happen? There'll be a time when negative charge will come on this particular plate. On continuously increasing the voltage of that battery, this intensity of negative charge on the plate will keep on increasing. The electrons which were coming in this direction, they will keep on experiencing more and more repulsions. They'll keep on experiencing more and more repulsions. There will be a voltage, there will be a reverse voltage at which the most energetic electron will also stop. And that voltage at which the most energetic electron will stop, that voltage is something which you call as a reverse voltage. Yes? Right, people? Is it clear? Did you get the idea of reverse voltage? I mean the stopping potential which I'm talking about. Stopping potential. So what is the stopping potential basically? What is the stopping potential? Guys, if you still have doubts here, let me make it further clear to you. If you still have doubts here, let me make it further clear to you. See, this was basically your positive plate. This was basically your positive plate, right? This was your positive plate. It was connected with this particular battery. Now imagine, just try to understand in this way. Imagine I'm connecting this with one more external battery, and this is negative terminal now, this is positive. If this is negative, if I keep on increasing the voltage of this particular battery, keep on increasing the voltage of this particular battery, the intensity of negative charge on this plate will increase. The intensity of negative charge on this plate will increase, right? And these electrons, which were supposed to come in this direction, they'll experience more repulsions, right? On increasing the voltage of this battery, can I say there will be one voltage at which the most energetic photoelectron will stop. And that voltage at which, that reverse voltage which we are giving, at which the most energetic photoelectron will stop, that reverse voltage is something which you call a stopping potential, right? That's something which you call a stopping potential. Okay, that's called a stopping potential. Right, guys? So what is the stopping potential? It is the reverse voltage which is applied to stop the most energetic photoelectron from reaching anode. Perfect. Now, my dear students, just try to understand. Just try to understand. What would have happened? The electron was coming out from the surface, for example. It had to reach here. It had to reach here. But due to the negative charge, this electron is experiencing repulsions. So when the electron comes out of this particular surface, it's moving. Now the electron is experiencing repulsions from this plate, right? It's experiencing repulsions from this plate. So what is happening to its kinetic energy? Kinetic energy of electron is decreasing. There'll be a point when the electron comes to the rest. When the electron comes to the rest, can I say when the electron comes to the rest, can I say entire kinetic energy of the electron has got converted into its potential energy? When the electron comes at the rest, I'll say entire kinetic energy has got converted into its potential energy. Potential energy is equal to EV naught. E is the charge on the electron, V naught is the stopping potential. Right? As per the work energy theorem, since electron was supposed to move, but it's experiencing repulsions, right? It's experiencing repulsions. So its motion is being distorted by the repulsions. That means its kinetic energy is getting converted into what? Potential energy. When it stops, entire kinetic energy would have got converted into potential energy. Potential energy of the electron is going to be charge on electron multiplied by stopping potential, right? So if maximum kinetic energy of the photoelectron is equal to EV naught, this V naught is the stopping potential. It is not the threshold frequency, right? So from the equation, this was our photoelectric equation. In this particular equation, you can replace this particular term. Instead of Kmx, you can write EV naught. You can write EV naught. Perfect. You can write EV naught. And my dear students, instead of incident energy, you can write h nu. Instead of phi, you can write h nu naught. And this is EV naught here. This is one more equation from which question can come. One more equation from which question can come. Now, my dear students, try to understand one thing. Just understand it. if you increase the energy of the incident photon, okay, let me keep it simple. If you increase the frequency of the incident photon, if you increase the frequency of the incident photon, that means energy of incident photon will increase, right? And as the energy of incident photon increases, kinetic energy of the photoelectron, that increases. As the kinetic energy of photoelectron increases, what happens to that reverse voltage? Stopping potential. Stopping potential, will it increase or decrease? Stopping potential will automatically increase, right? Because now we have to provide more reverse voltage to stop that high energetic electron. Yes? Right, people? Sophie, that's already taught. You can check mole concept part 3. Go to the playlist. Right, people? I believe it's clear. I believe it's clear, right? Yeah. So on increasing the frequency of the incident light, what happens to the stopping potential? Stopping potential increases. Perfect. And this is the equation which you are going to remember. See guys, let me write the equation again. Incident energy is equal to work function plus kinetic energy maximum, right? Now instead of kinetic energy maximum, what you can write? Instead of kinetic energy maximum, you can write E V0, where V0 is not the threshold frequency, it's the stopping potential. This is the same photoelectric equation in different format. Right? Now, if you want to make a graph between, this is stopping potential versus incident frequency. What the graph will look like? See guys, it's simple. It's very simple. Look at this particular equation. Can I say from this particular equation, EV0 is equal to H nu minus H nu naught? Absolutely. Can I say V0 is equal to H divided by E nu minus H divided by E nu naught? Absolutely. I'm plotting a graph between stopping potential and frequency of the incident light. This and this. This is plotting along y-axis. This I'm plotting along x-axis. So this automatically becomes your M. This whole term becomes your C. Sign in between is minus. So y is equal to mx minus c. Y is equal to mx minus c. Again, a straight line, but not passing through the origin. It's starting down the origin. This is the origin, for example. It will start from here. So this is the line. This is the graph. The distance from origin till the point from where the curve starts, that's something which you call as intercept. Intercept is denoted by C. C is equal to H nu naught by E. This intercept is equal to H nu naught divided by E. If I talk about the slope of this particular curve means M is equal to H by E. Slope of this particular curve is equal to M and M is equal to H by E. This curve you should also remember from now onwards. Okay. So my dear students, what all things we observed till now? On increasing the frequency of the incident light, kinetic energy of the photoelectron increases, stopping potential also increases. Right? Look at this particular question. Light of wavelength 400 nanometers is incident on metal with work function 2.3 electron volts. Calculate the stopping potential. V0. Basic equation you know. Incident energy is equal to phi naught plus Ke max. Instead of Ke max, you can write EV0. V0 you have to calculate. That's it. Now, incident energy is equal to Hc divided by lambda is equal to, this particular term already you know. This is 2.3 electron volts, right? Plus E V0. Right, guys? Now, Hc. What is Hc? 124. It is in nanometers, right? So, 1240 electron volt nanometer divided by lambda. How much is lambda? Lambda is 400 nanometer is equal to 2.3 electron volt plus electron V0. Perfect, guys? Perfect. Now see what all things I'll be cancelling here. So nanometer, first of all cancelled. This E, in short, cancelled. So what do I get? I get V0 is equal to, this particular term will be how much? This will be approximately 3, right? This will be 3.1. So it's going to be 3.1 minus 2.3 volts, right? So V0 is equal to 0.8 volt. What is meant by this 0.8 volt? This is that reverse voltage. This is that reverse voltage which has to be kept. Then only the highest energetic electron will stop, that won't reach the anode. I believe it's clear. I believe it's clear. Right? Now, my dear students, there are a few more things. There are just 2 to 3 things more in photoelectric effect. Do you know what is intensity of light? How do you define the intensity of the light? How do you define the intensity of the light? Intensity is defined as energy incident per unit area per unit time. Energy incident per unit area per unit time. That defines the intensity of the radiations, of the light basically, of the source basically. Right? So what is intensity? Intensity is denoted by I. It is equal to energy which is incident on what? On a unit area of the surface per unit time. In a unit time, right? Now, imagine that the source is emitting radiations, light radiations. So energy which the light radiations will have, it will be equal to simply NHC divided by lambda, NHC divided by lambda, right? NHC divided by lambda multiplied by what? Multiplied by area of cross section, right? Multiplied by what? Multiplied by time. So this is the formula, first of all, by means of which you can calculate intensity, or you can write in terms of frequency as well. It is NH. C divided by lambda is your nu, right? This is A multiplied by T. So energy incident per unit area per unit time. That defines what? That defines your intensity. So if you look at this particular expression, your I, intensity, is equal to NH nu divided by A multiplied by T. Intensity of the light, intensity of the radiation, right? Intensity of the source basically. Intensity of the source. This N represents number of photons which the source sends. H is constant. Mu is the frequency of the light which the source sends, right? My dear students, try to understand. If you keep frequency constant, can I say at that point of time, intensity is directly proportional to number of photons emitted? Absolutely, intensity is directly proportional to number of photons emitted. It's evident. Intensity, if I keep the frequency constant, I'll say intensity that is directly proportional to number of photons. So, more the photons emitted by the source, more is the intensity basically. Right? More is the intensity. So I would say more the photons sent by the source, more is the intensity basically. Agreed? More is the intensity. Right? Perfect. So intensity, it depends on number of photons emitted by the source. More the photons emitted by the source, more is the intensity of the light. In short. Yeah? Okay, one more thing. My dear students, try to understand one simple thing. If you have to measure the photocurrent, how do you get the photocurrent? I is equal to Q by T. Q is the charge which goes to the anode in the form of electrons. T is the time. This charge, you already know it's Q. Q is equal to Ne. N is the charge on electron. N is the number of electrons which goes towards the anode. T is the time taken. This is the formula by means of which you can calculate the photocurrent as well, right? Well, we have got nothing to do with this. Leave it aside. But here are some graphs. Which you have to understand. My dear students, both kinetic energy and stopping potential of photoelectrons varies with the frequency of the incident light. Something which we have discussed. If you increase the frequency of the incident light, kinetic energy of the photoelectrons increase, due to which stopping potential also increase. So both increases. These two graphs which we have discussed already. Right? Let's have a look on few more things. Now, what happens to the kinetic energy of photoelectrons upon changing the intensity of the light? Imagine you're increasing the intensity of the light. My dear students, when you increase the intensity of the light, that means you are increasing, that means number of photons number of photons emitted are increasing. Number of photons emitted are increasing. Nothing is happening to the energy of photons. Nothing is happening to the energy of photons. If you increase the intensity of the light, that means you are increasing the number of photons emitted, right? But nothing is happening to the energy of light. It's same. Since you know one photon is enough to knock out one electron. Since you know one photon is enough to knock out one electron. If you increase the energy of the incident, if you increase the intensity of the light, that means more photons are incident on the metal surface. One photon is enough to take out one electron. If more photons are incident on the metal surface, can I say more electrons will emit? If more electrons emit, that means more charge will go towards anode. That means more will be the photocurrent. More will be the photocurrent. Right? More is the photocurrent. Is this clear? Is this clear, guys? Right? So, I can simply generalize one statement. If you increase the intensity of the light, photocurrent increases. Photocurrent increases. Yeah? When you increase the intensity of the light, I'll simply say photocurrent will increase. Photoelectric current will increase. Okay, tell me one thing. When you increase the intensity of light, will anything happen to the kinetic energy of the photoelectron? Nothing will happen to the kinetic energy of the photoelectron. Nothing will happen to the stopping potential. Right? Nothing will happen to the stopping potential. Okay? I believe this is clear. So on increase the intensity, the kinetic energy of the photoelectrons, it remains unchanged. It remains unchanged. Let me quickly summarize few points. Right? So my dear students, the first point. If you increase the frequency of the incident light, that means you are increasing the energy of the incident light. What will happen due to that? Due to that, kinetic energy of the photoelectron will increase. Due to that, stopping potential will also increase. Point number one. Right? Point number one. Point number two. When you increase the intensity of the light, what will happen to the energy of the photons? It remains the same. Energy of the photons remains the same. But number of photons incident on the surface will increase. Since one photon is enough to take on one electron, if more photons are incident, that means more electrons will be emitted. More electrons will be emitted. So number of photoelectrons will be more. Number of photoelectrons will be more. More the photoelectrons, more will be the photocurrent. More will be the photocurrent. More will be the photocurrent. Right? Perfect. One more thing. If intensity is increased, if intensity of light is increased, nothing is happening to the energy of light. It remains the same. If incident energy remains the same, kinetic energy remains the same. Kinetic energy remains the same. Stopping potential, it also remains the same. So this is the nutshell. This is the nutshell, my dear students. Is all clear? Okay. So this was your Planck's quantum theory and photoelectric effect. I believe it's clear to everyone. And Bohr's theory will start in the next session. Your next session is day after tomorrow, guys. Okay? Your next session is day after tomorrow. So day after tomorrow, let's start the Bohr's theory, right? That is one of the most important topics of this particular chapter. Do let me know in the comment section of this particular video if all the things are clear, if you got the feel of all the things which we discussed in the today's session. Okay? It was nice meeting you. Let's catch up in the next session, guys. You take care. God bless you all. Bye-bye.